Welcome to our nocturnal laboratory of gentle discoveries. Here at Dreamtime Science, we transform complex concepts into lullabies for the curious mind. You know what's fascinating? I've been thinking about how water, something so simple and familiar, behaves in ways that almost feel magical, like how ice floats instead of sinking. There's something remarkable about this gentle quirk of nature that quietly shapes our whole world, and I can't wait to share why it happens and what other watery mysteries it connects to. It's like discovering a secret hidden in something we see every day. Should you find solace in these cosmic lullabies, consider becoming a regular dreamer by subscribing. Share what topics intrigue your curious mind in the comments below. Now, take a moment. Adjust your blanket. Find the perfect hollow in your pillow. Let your shoulders melt. Breathe in and out. Just as dusk settles and the world hushes to a gentle murmur, there is a peculiar comfort in recalling the simple wonders that surround us. Those everyday miracles so woven into the fabric of our lives that we often forget to marvel at them. Chief among these is the sight of ice afloat, drifting lazily atop a glass of water or stretching, vast and white, across the skin of a winter lake. Not sinking, as might seem natural, but buoyed up by some subtle arrangement of nature's laws. This oddity, this quiet rebellion against expectation, has haunted our stories, our science, and our dreams for centuries. To appreciate the full weight of this phenomenon, it is worth considering how deeply the image of floating ice is etched into the collective memory of our species. It surfaces in creation myths, in tales of survival and exploration, and in the speculative realms of science fiction, where laws of physics are both playthings and anchors. The sight of a frozen surface bearing the footprints of a fox or the shadow of a skater is more than a seasonal curiosity. It is a stage upon which countless dramas have unfolded, both real and imagined. Begin, if you will, with the ancient storytellers. In the cold north, among Sami herders and Inuit hunters, the arrival of winter's ice was not simply a meteorological event, but a transformation of the world itself. Rivers and lakes, once fluid and treacherous, became solid highways, opening new paths for sleds and wandering feet. The floating ice, a thin silver skin, separated the known from the unknown, the living water below, teeming and mysterious, from the brittle certainty of the surface above. To step onto this threshold was to cross into a liminal realm, a place where the ordinary rules of movement and safety were rewritten with every crack and whisper. Here and there in ancient mythologies, ice is a force both feared and revered. In the Norse cosmos, the primordial void, Ginnungagap, was bordered by the realm of fire and the realm of ice, Muspelheim and Niflheim, whose meeting birthed the world itself. This collision of heat and cold, of frost and flame, is more than a story about the origins of everything. It is a meditation on transformation, on the way elements combine and recombine to make the improbable possible. Ice, in these stories, is never simply inert. It is alive with potential, with danger, with promise. Yet the true strangeness of ice, its refusal to sink, has always captured a special fascination. For in most other substances, the solid state is denser than the liquid. A lump of solid wax, for instance, will sink in its molten pool, and a shard of solidified lead will plummet through its own heavy melt. Not so with water. Here the solid is lighter, more buoyant, floating serenely on the liquid below. This is a curious inversion, a riddle posed by the universe with no easy answer. In the quiet hours of early science, thinkers and alchemists puzzled over this oddity. Aristotle, in his treatise Meteorologica, mused on the nature of water and its transformations, proposing that the cold, by expelling heat, caused water to stiffen and become less heavy. The explanation, though incomplete, captured the sense of mystery that still clings to the phenomenon. Why should ice float? Why should lakes freeze from the top down, preserving the life below rather than solidifying from their depths, suffocating all in a crystal tomb? Centuries later, as the lens of science grew sharper, experiments replaced speculation. In the laboratories of the Enlightenment, glass vessels and careful measurements revealed that water reaches its maximum density at 4 degrees Celsius, and that as it cools further, it expands, a property shared by few other liquids. The crystalline structure of ice, with its open hexagonal lattice, traps more space between molecules than the jostling fluid dance of liquid water. This arrangement, invisible to the naked eye, is the secret to ice's buoyancy. Each flake and shard is a marvel of geometry, a cathedral of emptiness, rising against gravity's pull. Yet before the microscope and the thermometer, this was a mystery to be pondered through story and metaphor. In the long, dark winters, tales grew up around the ice, of spirits and ancestors sealed beneath the frozen surface, of messages and omens borne on drifting floes. The floating of ice became a metaphor for endurance, for concealment, for the fragile boundary between worlds. In Russian folklore, the spring thaw is the time when the ice breaks, not only in the rivers, but in the hearts of men, releasing what has been hidden or repressed. In the literature of exploration, the floating ice is an antagonist and a companion. Consider the journals of polar adventurers, those who braved the Arctic's white wilderness in search of passage or glory. The ice was both a promise and a threat, a force that could bear a ship aloft or crush it to splinters. Sir Ernest Shackleton's Endurance drifted for months, locked in the pack, riding the slow, inexorable currents of the Weddell Sea. The men learned to read the ice's moods, the creaks and groans, the sudden thunder of a floe splitting apart. To them, the fact that ice floated was not a curiosity, but a matter of survival, a floating continent that allowed life to persist in places where none seemingly should. Science fiction, too, has been drawn to the metaphorical and literal implications of floating ice. In the speculative worlds spun by writers and filmmakers, water's peculiarities become keys to new frontiers. Imagine, for a moment, a frozen moon orbiting a gas giant, Europa, say, with its icy crust sheltering a hidden ocean. What if the ice above, light and buoyant, floats atop a vast alien sea, concealing secrets from the probing eyes of distant explorers? The floating ice becomes a gateway, a shield, a testament to the possibilities of life in the most improbable places. Arthur C. Clarke, in his novel 2010 Odyssey 2, immortalized this vision, describing the cracking and shifting of Europa's ice as the prelude to discovery. The floating crust, miles thick, both hides and hints at the life that might stir in the darkness below. Here, the old terrestrial marvel is writ large across the cosmos, inviting us to dream not only of what is, but of what might yet be. In more whimsical tales, the oddity of floating ice takes on a surreal dimension. Consider the frozen cities of Italo Calvino, suspended above rivers that never thaw, or the ice-locked planets of Ursula K. Le Guin, where societies are shaped by the rhythms of freeze and thaw. In these stories, as in reality, the floating of ice is not merely a quirk of physics, but a force that shapes destinies, dictates migrations, and inspires both awe and trepidation. Even in the realm of children's tales and animation, the image of floating ice is potent. When Walt Disney's Frozen unfurled its tapestry of snow and longing, it did so atop the enduring symbol of an icy lake, a place where secrets are kept and transformations are made possible. The hero's journey across the shifting, treacherous surface is an echo of countless real and imagined crossings, a metaphor for change, for danger, for the thin line between safety and the unknown. These cultural echoes are not confined to the north or to the distant past. Across the continents, in places where winter is a fleeting guest, the spectacle of floating ice, be it in a glass of lemonade or on the surface of a rare frozen pond, retains its peculiar charm. It is a reminder that the ordinary is often stranger than we realize, that the laws of nature are full of riddles waiting to be unraveled. But the fascination with water's oddities does not end with ice. The very behavior of liquid water is a source of endless curiosity. Water, for all its ubiquity, is a substance of contradictions. It is capable of dissolving more substances than any other liquid, earning its title as the universal solvent, and yet it refuses to dissolve itself. It can carve canyons from stone, yet evaporate at a whisper. Its surface, drawn tight by invisible forces, allows insects to skate and beads to form, a dance of tension and cohesion that shapes the world in ways both subtle and profound. In science fiction, these properties become engines of plot and possibility. Writers imagine worlds where water behaves differently, where it is heavier as a solid perhaps, and lakes freeze from the bottom up, entombing life beneath layers of ice. Such worlds are at once familiar and alien, reminders of how finely tuned our own planet's chemistry must be to permit the forms of life we know. Some have speculated, with a shiver of poetic dread, on what might have been if water did not behave as it does. If ice sank, lakes and rivers in winter would become solid from the bottom up, extinguishing the creatures that hibernate in the mud, shattering the cycles of renewal that sustain forests and fields. The floating of ice is not a mere curiosity, but a safeguard, a quirk of molecular geometry that preserves the possibility of life through the long, cold months. In the luminous language of the poet, water is a mirror, a memory, a shapeshifter. It holds the sky and the stars in its surface, and it cradles the past in every drop. The floating of ice, then, is more than a physical fact. It is a moment of equilibrium, a reminder that the world is full of gentle surprises. To this day, the image of floating ice continues to inspire. Artists capture its delicate translucence, its fleeting patterns, its quiet defiance of gravity. Photographers wait for the perfect moment when the setting sun turns a frozen pond to gold, or when a lone iceberg drifts across a silent bay. In these moments, the ancient wonder persists, undimmed by explanation. And so, as night deepens and the mind drifts toward dreams, think of the stories that float atop our memories, light as frost, buoyed by the strangeness of the world. Recall the explorers lost and found, the children skating on thin ice, the poets and scientists and dreamers who have paused to wonder at the ordinary miracle of ice that floats. The story of water's oddities is far from finished. It is a current that runs beneath the surface of our understanding, inviting us to follow where it leads. For just beneath the floating ice, in the restless molecules and silent depths, new stories are always stirring, waiting for the next question, the next unlooked-for revelation, the next act in the unfolding drama of this most peculiar and essential of substances. Beneath the apparent simplicity of a drop of water, beneath even the glistening dance of a snowflake in the winter air, there lies a small but mighty secret, one that shapes the grandest rivers, the deepest lakes, and the very cycles upon which life depends. It is a secret woven not from myth, but from the peculiar arrangement of atoms and the silent, persistent pull of invisible forces. To understand why ice floats, why frozen ponds cradle skaters atop their glassy surfaces, or why fish can survive beneath wintry covers, we must first journey inward, to the world of the water molecule and its astonishing polarity. Within the realm of chemistry, all begins with the atom, the unassuming building block of all matter. Water, known to science as H2O, is composed of 2 hydrogen atoms and 1 oxygen atom, bound together by the allure of shared electrons. At first glance, this seems unremarkable. Hydrogen is the lightest element, a single proton wrapped in its tiny shroud of energy, while oxygen holds 8 protons in its heart, with an appetite for electrons that far exceeds that of hydrogen. What unfolds when these atoms meet is not simply a union, but an asymmetric embrace, one that gifts water with its extraordinary character. The oxygen atom, with its voracious hunger for electrons, draws the shared pairs in the molecule closer to itself, leaving the hydrogen atoms somewhat bereft. This unequal sharing is the root of polarity, a term that might evoke images of north and south poles, and indeed it is not so different. In the water molecule, a subtle separation of charge emerges. The side where the oxygen sits becomes slightly negative, while the hydrogen-laden side becomes slightly positive. Imagine, if you will, the water molecule as a tiny bent figure, its two arms outstretched, each tipped with a hydrogen. The angle between these arms, about 104.5 degrees, gives the molecule its shape, not linear, but askew, and it is this angular form, combined with the uneven tug-of-war over electrons, that defines its polar nature. Polarity is more than just a curiosity. It is a force that shapes the behavior of water on every scale. Because each water molecule has a positive and negative end, they behave as miniature magnets attracted to one another's opposite charges. This attraction is called the hydrogen bond, a connection far weaker than the robust bonds that hold atoms together, yet strong enough in great numbers to sway the properties of water itself. Hydrogen bonds are fleeting, lasting only trillionths of a second before breaking and reforming elsewhere. But in the collective dance of billions upon billions of molecules, they produce effects both subtle and profound. The polarity of water explains much that we experience and much that we take for granted. It is why water beads upon a waxy leaf, why it climbs the narrow vessels in a plant's stem, and why it dissolves salt with ease. But perhaps the most enchanting of all is the paradox of ice floating, an anomaly among liquids, for most substances grow denser as they solidify. To uncover why water defies this expectation, we must follow the consequences of its molecular polarity into the world of solidification. On a warm day, water molecules skitter and spin, their thermal energy propelling them through a liquid maze. Each molecule forms and breaks hydrogen bonds with its neighbors, never fixed in place, always in flux. But as the temperature falls, their motion slows. The energetic jostling gives way to order, and the molecules begin to settle into a lattice, a repeating pattern that will become the crystalline structure of ice. Here, the true influence of polarity reveals itself. The bent shape of the water molecule, coupled with its partial charges, dictates that each molecule seeks to form hydrogen bonds with as many as 4 neighbors, arranging themselves in a loose, open framework. Picture this lattice not as a compact, crowded structure, but as something airy and expansive. The molecules, locked in their hydrogen-bonded embrace, must keep a certain distance from one another, farther than they do in the liquid state. The result is a crystal with more space between its constituents, an architecture with pockets of emptiness, like the delicate scaffolding of a snowflake. This open arrangement means that ice is less dense than water. It occupies more volume for the same mass. And so, when ice forms upon a pond or a river, it floats, riding atop the denser liquid below. This floating is more than a mere oddity. It shapes the fate of lakes, rivers, and even the climate of continents. In the depths of winter, when the air cools and the surface waters begin to freeze, the forming ice insulates the water below, slowing further freezing and preserving a refuge for life. If ice sank, the cold would creep inexorably downward, freezing the entire body of water solid, extinguishing aquatic life in its icy grip. But thanks to the peculiar polarity of the humble water molecule, the world is spared such a fate. Let us delve deeper still into the geometry of the ice crystal. The most common form, known as hexagonal ice, arranges its molecules in a 6-sided pattern. Each water molecule forms hydrogen bonds with 4 others, 2 through its hydrogen atoms and 2 through the lone pairs of electrons on the oxygen. The resulting structure is a tessellation of hexagons, repeating in all directions, their open spaces giving rise to the familiar six-pointed symmetry of snowflakes. No two snowflakes are alike, for their growth is shaped by the whims of temperature and humidity, but all share this underlying architecture, a testament to the quiet insistence of polarity. Even in the liquid state, water is not wholly without order. Short-lived clusters form and dissolve, molecules joining hands before parting ways. These transient structures give liquid water some of the properties of a solid, lending it surface tension and the ability to flow in narrow channels. Yet it is only upon freezing that the full extent of water's molecular choreography is revealed, as randomness gives way to crystalline precision. But consider for a moment what might have been. If the angle between the hydrogen atoms were different, if the pull of oxygen on its electrons were less, the polarity of water would change, and with it the entire nature of ice. The lattice might collapse into a denser form, and ice would sink, as it does for most other substances. The consequences would ripple through the natural world. Lakes would freeze from the bottom up, and the cycles of life that depend on liquid water through the coldest months would falter. All this balanced upon the fine point of a molecular angle and the subtle asymmetry of charge. The story of water's polarity is also a story of connection. The same hydrogen bonds that hold ice aloft in a pond are responsible for the cohesion that lets water climb the tallest trees. In the xylem vessels of a redwood or a eucalyptus, water molecules pull upon one another, forming an unbroken chain from root to leaf, defying gravity through the quiet power of collective attraction. The surface tension that allows a water strider to dance upon a pond, or a droplet to hold its shape upon a leaf, arises from the same invisible embrace. Polarity also endows water with its remarkable solvency. Positive and negative charges on its surface allow it to surround and separate ions, dissolving salts and minerals with ease. It is why rivers carry nutrients from mountain to sea, why blood can transport oxygen and waste, and why the chemistry of life itself unfolds in watery solution. The capacity to dissolve, to transport, to connect. These are all gifts bestowed by the simple, asymmetrical dance of hydrogen and oxygen. And yet, for all its power, polarity is a fragile thing, easily altered by changes in temperature or pressure. Beneath the surface of every pond, every ocean, the balance between order and chaos is in constant play. When water freezes, it expands, and the ice that forms above acts as a shield, slowing the escape of heat from the water below. It is a shield that enables fish to swim beneath the ice, to seek out the dim winter sunlight, and to await the thaw of spring. The floating ice, born of molecular polarity, becomes a cradle for life. Let us linger, if only for a moment, on the boundaries where water's phases meet. At the surface of a lake in winter, the air chills the uppermost layer, causing the water molecules to slow and draw closer together. As they approach the freezing point, they arrange themselves into the crystalline lattice of ice, expanding and rising to form a lid upon the liquid below. This process is not uniform. Currents and winds stir the water, and temperature gradients create layers of varying density. But always the result is the same. Ice floats, and life finds sanctuary beneath. Even the forms of ice are varied, shaped by the conditions under which they grow. In the polar regions, vast sheets of sea ice drift atop the ocean, their undersides sculpted by currents, their surfaces etched by wind. In the laboratory, scientists can coax water into forming different types of ice, some denser than liquid water, some even lighter than the familiar hexagonal form. Each structure is a testament to the flexibility of hydrogen bonding, to the ways in which polarity can manifest under different pressures and temperatures. The story of ice and its floating is not confined to Earth. On distant moons, such as Europa and Enceladus, thick shells of ice cover oceans that may harbour the ingredients for life. There too, the peculiar polarity of water shapes worlds, insulating subsurface seas from the chill of space and perhaps providing a stable refuge for unknown forms of life. In every snowflake, every frost-laced window, every pond sealed by winter's hand, the same molecular tale unfolds. The bent shape of the water molecule, the uneven pull of its electrons, the constant shifting dance of hydrogen bonds, these are the threads from which the world's most vital fabric is woven. The floating of ice is not an accident, nor merely a curiosity, but the inevitable consequence of deep, unseen forces that operate at the smallest scale, yet whose influence ripples outward to shape the very face of the planet. And so, as night falls and the world cools, as frost creeps across the fields and the first thin layer of ice forms upon the pond, we are witness to the handiwork of polarity. The molecules, obedient to their nature, arrange themselves into a lattice both strong and delicate, open and buoyant, rising above the denser waters below. It is a quiet miracle, repeated 1 trillion times in every winter, a reminder that even the smallest asymmetry can have echoes on the grandest stage. Beyond the floating ice and the hidden geometries of water, there are further mysteries to ponder. Polarity not only shapes the behavior of water in its pure state, but also governs its interactions with other substances, its role in the chemistry of life, its capacity to dissolve and to bind. The subtle charge separations that set water apart are the very same that allow it to cradle ions, to form the basis of cellular machinery, to serve as the medium through which life's reactions unfold. And as we drift further into the heart of water's story, we find that the peculiar polarity of its molecule is but the threshold to a deeper world, a world where the boundaries between solid, liquid, and gas blur, where energy is stored and released, where the cycles of freezing and melting govern the rhythms of climate and the persistence of life. In this world, the consequences of polarity ripple outward from the shape of a snowflake to the fate of oceans, from the survival of a wintering fish to the chemistry that animates our very cells. Thus, as the ice forms quietly over the pond, as the first stars appear in the winter sky, the tale of water's polarity continues, poised between order and chaos, between structure and flow, promising yet more wonders in the chapters that await. We return to the world of water and ice, not as distant dreamers, but as curious explorers, ready to press our noses to the frosted glass and gaze deep into the very lattice-work of matter. Water, so familiar in the cup or the clouds, becomes a new and dazzling frontier when we ask, how do we truly know its hidden inner forms? How can we, with all our human limitations, hope to see the architecture of ice or the restless dance of water molecules? For millennia, our ancestors could only wonder. They saw ice glinting on ponds, snowflakes settling in silent spirals, the cold bite of frost on window panes. They saw the transformation, liquid to solid, vapor to droplet, but the process itself was shrouded in mystery. The shapes of snowflakes, so intricate and fleeting, hinted at some inner order, some invisible script written by nature's hand. But to read that script, to truly crack the crystal code, would require both ingenuity and patience, and above all, it would demand new tools, extensions of our senses, ways to peer into the microscopic and the secret. Consider for a moment the earliest attempts to probe these mysteries. Before electrons whirred through microscopes, before X-rays sliced through matter, there were only the simplest tools, a magnifying glass, a candle, the keen eye of a careful observer. In the 17th century, a curious astronomer named Johannes Kepler gazed at falling snow and wrote of their six-cornered perfection. He puzzled over why snowflakes always choose 6 arms, never 5 or 7. His treatise, On the Six-Cornered Snowflake, became one of the first scientific meditations on the geometry of ice, though he could only speculate about the forces at play. The true lattice, the hexagonal symmetry, lay far beyond the reach of his instruments. Then, in the centuries that followed, the lens-maker's art flowered. The microscope, at first a crude assembly of glass and brass, grew ever more refined. In the cold winters of the 19th century, a self-taught Vermont farmer named Wilson Bentley turned his microscope skyward. He caught snowflakes on black velvet and with breathtaking patience photographed them through his lens. Each image revealed a unique feathery star, never repeated, always six-armed, each arm a mirror of its siblings. Bentley did not yet understand the molecular logic behind this symmetry, but his work offered a first, fragile bridge between the macro world of our senses and the micro world of the crystal. Yet to truly understand the crystal code, to see how water molecules lock together in ice, or how they slip past one another in liquid, scientists would need to go even deeper. They would need to see not just the shape, but the structure, to map the invisible scaffolding that holds each crystal in place. The revolution came, as revolutions often do, from unexpected quarters. In 1895, Wilhelm Röntgen, a German physicist, discovered X-rays, strange invisible rays that could pierce flesh and reveal bones. Within a few decades, others realized that these same rays could do more than just peer inside the body. When fired at a crystal, X-rays would scatter, diffracted by the orderly ranks of atoms. The scattered rays would interfere, creating patterns, rings and spots, bright and dark, on photographic plates. These patterns, deciphered with mathematical care, could reveal the precise arrangement of atoms within the crystal. So it was that, in 1912, Max von Laue and his colleagues placed a tiny crystal in the path of an X-ray beam, and watched as the rays scattered and recombined. The resulting pattern, though abstract, was a fingerprint, a record of the internal symmetry and spacing of the crystal lattice. Soon after, father and son William Henry and William Lawrence Bragg developed the equations that would unlock these patterns. With their work, crystallography was born. Crystallography, what a word! It is both a science and an art, a dance of beams and shadows, mathematics and imagination. In a crystallographer's laboratory, a humble crystal, a sliver of salt, a speck of ice, becomes a stage for an invisible drama. The crystal is mounted, coaxed into position. A beam of X-rays, focused and sharp, is aimed with the precision of a surgeon's scalpel. The rays pass through the crystal, and on the far side a detector waits. The scattered rays strike this detector, creating a constellation of spots. Each spot encodes information about the distances and angles between planes of atoms inside the crystal. By analyzing the pattern, scientists can reconstruct the three-dimensional arrangement of atoms, like piecing together the scaffolding of a cathedral from the shadows it casts at sunset. Ice, it turns out, is a particularly beautiful subject for crystallography. Its molecules form a regular, repeating lattice, a network of hexagons, each oxygen atom bonded to four neighbors through delicate hydrogen bonds. In the most common form of ice, called ice-ich, these hexagons stack and interlock, creating the symmetry that Kepler once glimpsed in snowflakes. Crystallography has revealed the precise dimensions of this lattice, the distance between neighboring oxygens, the angles of the hydrogen bonds, the tiny deviations and distortions that arise as temperature and pressure change. But the story does not end there. X-ray crystallography works best with perfect regular crystals, orderly arrays that diffract the beam in predictable ways. Yet water, in its liquid state, is a chaos of motion. Its molecules tumble and whirl, forming and breaking hydrogen bonds 1 trillion times each second. How then to peer into the heart of liquid water? How to catch its shifting, ephemeral structures? Here, scientists have turned to new tools, neutrons, electrons, lasers, and the power of computation. Neutron scattering, for example, offers a way to probe the positions of atoms in amorphous materials, including liquid water and disordered ice. Neutrons, being neutral, penetrate deep into matter, and their scattering patterns provide clues about average distances and correlations between molecules. With careful analysis, researchers can reconstruct snapshots of water's fleeting networks, its clusters, chains, rings, though these images are always statistical, never as sharp or stable as a crystal. Another tool, the electron microscope, allows us to see the surfaces and edges of ice crystals with astonishing detail. A thin sliver of ice, cut by a diamond knife and kept at Arctic temperatures, is placed in the path of an electron beam. The electrons scatter and their trajectories are recorded, building up an image of the crystal's exterior, its facets, steps, and terraces. With advanced techniques, scientists can even watch ice grow and melt, layer by layer, molecule by molecule, as temperature and humidity are varied. The birth of a snowflake, once the subject of poetry and myth, becomes a slow-motion ballet, each move choreographed by the laws of thermodynamics. Lasers, too, have found their place in this quest. By shining beams of light through water or ice and analyzing how the light is scattered, scientists can deduce information about the size and shape of clusters, the vibrations of molecules, the dynamics of melting and freezing. Raman spectroscopy, for example, listens to the subtle shifts in frequency as light interacts with vibrating bonds. These shifts reveal the fingerprints of different phases, liquid, crystal, amorphous, and offer clues about the energy landscape of water. Yet perhaps the most transformative tool of all is computation, the ability to simulate, in silico, the behavior of water molecules over time. With powerful computers and clever algorithms, scientists can model millions of molecules, tracking their motions and interactions, exploring the vast possibilities of hydrogen bond networks. Molecular dynamics simulations, as they are called, allow researchers to test hypotheses, to visualize the birth of a crystal or the shattering of ice under pressure, to predict new and exotic phases that might be glimpsed in the laboratory. Through these tools, beams and particles, light and code, scientists have begun to crack the crystal code. They have mapped not just the familiar hexagons of ordinary ice, but the strange architectures that arise under different conditions. There is ice 2, compact and dense, formed under pressure, ice 3 with a more complex arrangement, ice 5, 6, 7, and beyond, each with its own symmetry, its own arrangement of oxygens and hydrogens. Some forms are so dense they can only exist at the crushing pressures found deep within planets. Others are so fragile they melt away unless kept at laboratory cold. Experiments have also revealed the mysteries of supercooled water. Liquid water chilled below its normal freezing point, yet somehow refusing to crystallize. In this strange state, water's properties become even more peculiar. Its density changes, its heat capacity spikes, and the bonds between molecules grow long and tenuous, as if the liquid is haunted by the ghost of the crystal it longs to become. Scientists have used microfluidic devices, tiny channels etched in glass, to trap droplets of water and chill them to these precarious states. By probing them with lasers and X-rays, they have watched, in real time, as the first seeds of ice form and grow, as the liquid surrenders to the inevitable crystalline order. But for all the power of these instruments, each reveals only a part of the story. The tools of science, wondrous as they are not omniscient. Each has its strengths and its limits, its windows and its blind spots. X-rays show us the average arrangement of atoms in a crystal, but not the fleeting chaos of the melt. Neutrons reveal the dance of molecules, but only in blurs and averages. Electron microscopes show surfaces, not interiors. Lasers tease out vibrations, but cannot capture the full three-dimensional geometry. Computation offers endless possibilities, but is always anchored to the accuracy of our models and the power of our machines. Yet taken together, these tools weave a tapestry, a multifaceted, ever-evolving portrait of water and ice. They allow us to move from the macroscopic, the snowflake in the palm, the ice on the lake, to the microscopic, the hydrogen bond, the cage of oxygens, the fleeting cluster in a drop. Each experiment is a question asked of nature, each result a clue, a fragment, a step along the path. And still the code is not fully cracked. There remain puzzles and paradoxes, gaps in our understanding, hints of deeper order. Why does water expand as it freezes when most substances contract? How do impurities and surfaces shape the birth of crystals? What is the nature of amorphous ice, the glassy forms found in comets and the cold void of space? How do the myriad phases of ice, stacked and layered in distant moons, shape the geology and the possibility of life? In laboratories around the world, the quest continues. Scientists grow single crystals of ice, measure their angles and faces, watch them melt under polarized light. They fire beams and pulses, tweak pressures and temperatures, record the scattering of photons and neutrons. They build models and run simulations, seeking patterns, testing theories, searching for the hidden logic beneath the surface. Each experiment is an act of faith, a belief that, with patience and ingenuity, the secrets of water and ice will yield themselves, if only for a moment, to our gaze. Each tool is an extension of the human senses, a way to reach into the invisible and bring back tales of structure and order. And as the data accumulates, as the patterns emerge, we find ourselves not at the end of the story, but at the threshold of ever deeper mysteries. The code is complex, its language written in the tensions between order and disorder, between crystal and melt, between the rigid and the fluid. To crack it fully may take not just new tools, but new ways of thinking, a synthesis of experiment and theory, of observation and imagination. Yet as the night deepens and the laboratory lights glow softly behind frosted windows, the work continues. The code beckons, unbroken, promising still more wonders to those who persist. And somewhere, out beyond the reach of microscopes and beams, the snow begins to fall, each flake a unique expression of the code, each one a challenge for the curious, each one a whisper of the secrets that await. Ice, life's raft. When winter's hush settles over the northern lakes, when the rivers slow and the world's high latitudes are draped in white, something quietly magical happens at the boundary between water and air. It is a phenomenon so familiar, so woven into the rhythm of our seasons, that its strangeness often escapes us, until we pause, as we do tonight, to let our minds drift beneath the surface. See the frozen pond at dusk, the last threads of gold and violet tangled in the sky, a brittle crust of ice growing outward from the shore, sealing in the liquid darkness below. The surface crackles faintly as it thickens, crystals knitting into a glassy shield. The world above is transformed, muffled by the snow, but beneath the ice, water remains liquid, cradling life through the coldest months. This simple persistence, that water beneath the ice stays unfrozen, is an accident of physics with consequences as profound as any in the history of the planet. Water, the most ordinary and extraordinary of molecules, chooses to disobey the usual rules. Most substances become denser as they freeze. Their atoms or molecules pack closer and closer, sinking as solids in their own liquid forms. But water, with its bent geometry and its insistent hydrogen bonds, does the opposite. As it chills, its molecules arrange themselves into a crystalline lattice, a repeating pattern that is spacious and open, creating more room between molecules than in the jostling liquid phase. The result? Ice floats. It is easy to underestimate what would happen if water behaved otherwise. Picture, for a moment, a world where ice was denser than liquid water, where each winter's freeze would send solid crystals plunging to the bottom of every pond, lake, and ocean. The surface would remain open, exposed to the bitter cold, and the next layer of water would freeze in turn, ice accumulating ever downward until the entire depth was locked in solid immobility. In such a world, the great aquatic ecosystems of Earth would be snuffed out each winter, their inhabitants entombed in darkness, unable to await the thaw. Life as we know it would be profoundly altered, perhaps impossible in the forms we cherish. Instead, the floating ice forms a delicate barrier, a raft upon which winter rides. It insulates the living water below, sheltering fish, insects, and myriad microscopic organisms from the full force of the cold. Under this accidental roof, life persists, slowed but unbroken, awaiting the sun's return. This property, this buoyant miracle, is neither inevitable nor universal. It is a quirk, an anomaly, a gift of molecular geometry. And from this gift springs a cascade of consequences, both biological and philosophical. Let us linger a while at the margin where ice and water meet, where the improbable lattice holds back the night. Here, under the translucent ceiling, the world is quieter. The water is cold, just above freezing, but it is alive. Tiny crustaceans dart through the gloom, their movements slowed but purposeful. Fish rest in the deeper layers, their metabolisms dialed low, riding out the famine of winter in a state of suspended animation. Even the microscopic algae and bacteria, which form the base of the aquatic food web, cling to existence, drawing what little light and nutrients they can from the muted world. Life under the ice is a study in resilience, in adaptation to a world defined as much by absence as by presence. Many fish, such as perch and pike, accumulate reserves of fat in autumn, storing energy against the long deprivation ahead. Insects spend their larval stages in the mud at the bottom, their growth arrested by the cold, poised to resume with the first warmth of spring. Some amphibians, like the wood frog, tolerate being partially frozen, their cells protected by antifreeze-like compounds that prevent lethal ice crystals from forming inside. Each species, in its way, is bound to the rhythm established by water's peculiar dance, by the sheltering raft of ice above. But the significance of floating ice is not solely biological. It is also a philosophical invitation, a reminder of the subtle ways in which the universe conspires to make life possible. The laws of physics are impartial, indifferent, yet here, in the arrangement of a simple molecule, a doorway is opened, a narrow path through which complexity and consciousness might emerge. It is tempting to see intention, to imagine a benevolence in the structure of water, but science teaches us not to ascribe will where there is only chance and necessity. Instead, we are called to marvel at the contingency, that in a universe of endless possibilities we inhabit a world where ice floats. This floating ice has shaped not only the survival of organisms, but the stories and myths that people carry. In northern cultures, the freeze and thaw of lakes signal the passage of time, the return of the sun, the promise of renewal. In the shattering of the spring ice, with its thunderous cracks and shifting slabs, people hear echoes of creation and transformation. The very possibility of these cycles, of death and rebirth encoded in the seasons, depends on that silent, buoyant raft. Consider the role of floating ice in the great cycles of the planet. When lakes and rivers freeze, the ice acts as a cap, limiting the exchange of gases with the atmosphere. Beneath the ice, oxygen levels slowly dwindle over the months. Some creatures perish, but many endure, drawing on reserves or entering states of torpor. When the ice finally melts, the sudden influx of light and warmth sparks a riot of activity. Algae bloom, insects emerge, fish feed, and birds return. The rhythm of life, so long suspended, resumes with explosive force. On a grander scale, floating ice is a guardian of climate. The vast expanses of sea ice in the Arctic and Antarctic reflect sunlight back into space, cooling the planet and stabilizing weather patterns. The ice acts as a shield, tempering the extremes of heat and cold, modulating ocean currents, driving the cycles that shape the world's climate. In a very real sense, the floating ice is both a symptom and a regulator of the planet's health, a mirror of balance teetering on the edge of change. As we peer more closely into the molecular world, we see that the uniqueness of water's behavior is a consequence of its polarity and the ways in which its molecules cling to each other. Each water molecule is shaped like a tiny boomerang, with 2 hydrogen atoms at one end and an oxygen at the other. The oxygen tugs the shared electrons closer, making it slightly negative, while the hydrogens are left slightly positive. These tiny electric charges mean that water molecules are drawn to each other, forming fleeting but persistent bonds, a ceaseless dance of attraction and repulsion. As water cools, these bonds settle into a more orderly pattern, an open lattice that holds the molecules apart, making ice less dense than liquid. It is a structure as beautiful as any snowflake, as intricate as the frost that feathers a window pane, and it is this structure, this accidental elegance, that makes ice a raft rather than a stone. In the far polar regions, the drama of floating ice is writ large upon the landscape. Sea ice forms in the autumn, spreading outward from the land in great white sheets. Beneath this frozen plain, the ocean teems with life. Tiny algae bloom on the underside of the ice, drawing energy from the weak, filtered sunlight. These algae feed zooplankton, which in turn sustain fish, seals, and the great whales that roam these waters. The entire food web of the polar oceans depends on the presence of ice, on the thin, shifting platform that floats between water and sky. The melting and freezing of sea ice are among the most visible expressions of climate's heartbeat. Each year the ice grows and recedes, its movement tracked by satellites and by generations of indigenous peoples who read the signs of the land and sea. The thickness and extent of the ice determine the migration of animals, the survival of young, the patterns of hunting and gathering. In this way, the floating ice is not just a scientific curiosity, but a foundation of culture and meaning, a teacher and a warning. There is a quiet wisdom in the way life has adapted to the paradoxical nature of ice. Some bacteria and archaea have evolved to thrive in the brine channels that form within sea ice, tiny liquid veins cradled in the frozen matrix. These microbes, called extremophiles, are among the hardiest organisms on Earth, surviving in temperatures far below freezing, in darkness and isolation. Their existence suggests that life may be possible even in the icy moons of Saturn and Jupiter, where water may lurk beneath the surface, protected by a shell of floating ice. Here, then, is the philosophical vista opened by the floating ice, that life, given the slenderest of chances, will find a way, that the properties of matter, shaped by laws indifferent to meaning, can nonetheless give rise to meaning, to persistence, to memory, to hope. The raft of ice is a metaphor, a reminder that fragility and resilience are not opposites but partners, that survival often depends on the most unlikely of shelters. For those who walk beside frozen rivers or skate across glassy ponds, the ice is both boundary and bridge, a threshold between worlds. It invites contemplation, a sense of connection to cycles far older and larger than any individual life. The creak and sigh of the ice, its translucent glow, the shadows that gather beneath. It is easy, in such moments, to feel the weight of time, the sweep of evolution, the delicate balance upon which existence rests. And so, as the night deepens and the cold settles in, let us linger a while longer at the edge of the ice. Let us listen to the quiet, to the faint stirrings of life beneath the surface, to the stories encoded in the crystalline lattice. For in the floating ice is a lesson that the world is shaped as much by its accidents as by its laws, that the extraordinary can spring from the ordinary, that life's raft may be fragile, but it endures, buoyed by the chance geometry of water, held aloft by the cold and the dark and the promise of another spring. The journey continues, unbroken, beneath the sheltering ice. As our journey through the shimmering secrets of ice drifting softly to a close, we watch its comet tail fade gently into the hush of space. May the quiet wonder of water's mysteries cradle your dreams tonight, inviting you to return soon for more gentle tales woven from the stardust of science.